Welcome to the Continuous Integration / Continuous Development tutorial. What you're seeing on the screen right now is a Chrome browser on the left side and a Mac terminal on the right side. On the left side for the Chrome browser, I have it open to the HSF training tutorial page that you should already have gotten a link to when you register for the workshop. As you can see, it's pretty well complete, especially for the pipeline section on CI/CD, and there are quite a few sections to go through to get through everything. And the series of videos that we are going to be going through here will be covering everything that you see on this page, except for the coffee breaks. So, the very first thing that we're going to be doing is going over to the setup here. If you have already set up the code that you need for the pipeline, feel free to skip this video, but I'll be sad. If you have not set up the code that you need for the pipeline, or you are unsure that you have set up the code, go ahead and keep watching this video. The very first thing we need to do, as an aside, I should remind you that a lot of this is on GitLab. And if you have a GitLab with some other organization, such as Fermilab or Argonne or Brookhaven, go ahead and use their GitLab instance. But you should be able to do the same thing no matter which GitLab instance you're using. So what I'm going to go ahead and do is use everything here on the GitLab instance. So the first thing that we need to do is to get the code. So I'm going to scroll down a little bit, and there's this little sentence about where we haven't set up the payload yet. So I'm going to go ahead and click this GitHub link that I have here. This will open up the GitHub page that we have, and this GitHub page has this entire payload that we need, and there's a lot of instructions here. So what we're going to do is a very nice way. We're going to go ahead and click on this green button on the top right, and we're going to go ahead and copy this URL. Now, in my terminal on the right side, I'm going to go ahead and clone that URL. And now that we've cloned the URL, we're going to go ahead and enter this directory that we just made. If I go ahead and look at the remotes that I have here that exist on this, we can see that the origin is the URL that I used to clone. What I'm going to do instead is to rename this origin remote to a new remote that I create. So, back on this left hand side, I'm going to go to my GitLab instance under my name, or you can just go straight to the GitLab instance. At the very top of it, I'm going to go ahead and click this little plus icon here, and go ahead and click on new project, because I want to create a new project. This should go ahead and it's going to fill in the default project URL under my namespace, which in this case is gstart. We're going to call this new project that we want to create Virtual Pipelines Event Selection, and so that'll also be the project slug that gets created. And one last thing that I want to point out, if we go back to the setup description, you see on this bottom here I have this little excerpt about the repository permissions. Note that you want to make sure that the visibility level for your repository is set to public for whichever one you create. You want to make sure that your repository is public so that other people can see it too, including the mentors and instructors who will be around to help you. So we're going to go ahead and click Create Project, and we're going to create a public project. In this case, it has created my public project called Virtual Pipelines Event Selection. So I'm going to go ahead and get this clone URL that I created here at the top left by clicking that blue button and grab the clone URL. And then I'm going to go back into this terminal, and instead of cloning this time, what I'm going to do is rename the origin URL. So I'm going to do git remote set -URL origin and paste it just like that. Now, if I look at the git remote v again, it has renamed it to my GitLab URL g/virtual pipelines event selection instead of the previous remote, which was the HSF training CMS analysis. Alright, so now once I've done that, I'm going to go ahead and push it to the origin and also set the upstream branch. And that means it should just track it using the new origin that I've created. Now, once I push this, I should be able to go ahead and refresh the page that I have on the left-hand side. And I should be able to see all these files that have been created here, as well as the various 20 commits that are included. So that's good. So once you're at this point, we're ready to go ahead and continue with the CI/CD the CI/CD tutorial. Again, if you have any questions or if you are stuck at this point, feel free to talk to your mentors and ask questions. Is going to be about the introduction, introducing you to what exactly CI/CD is and what it generally means to you. What you see on my screen is a terminal indeed, but we're not going to be using that for this section. But I leave this in a split screen for consistency among all my videos. On the left side in the browser, which I'm scrolling through right now, is the tutorial page from the awesome bootcamp that we hosted in February is certain. So we're going to go ahead to the introduction part. And the goal of the introduction is to explain what CI/CD is, and you'll be able to understand by the end of this video all the different resources to explore this more in depth to your own liking. Note that we don't particularly require that you use a particular solution. However, we will generally encourage GitLab for all the CI/CD work that we're doing in this tutorial. But there are other solutions which I will mention towards the end of this video. So CI/CD itself is broken up into two pieces. The CI part is the continuous integration part, and that is the literal continuous integration of code changes that you make. Those code changes could be, for example, analysis code, or code that you use for plotting in your offline analysis, maybe doing a statistical fit or doing some histogramming. It could be, for example, LaTeX code that you're using to write up a document and you want to make sure that the document still compiles or that you're not missing anything. It could be, for example, that you're building a website using HTML, CSS, and JavaScript, or some other language such as Node or Ruby, and so on, and you want to make sure that the website still builds in a way that you can deploy. Which leads to the second part, the CD part, the continuous deployment. And continuous deployment is about the literal continuous deployment of code changes. The idea is that as long as the CI passes, that you've done all the tests and checks that look great, then you can go ahead and deploy all of those changes live. Deploying is a general phrase where it can mean, for example, if you have analysis code and you pass all of your checks, such as your flow checks and your physics checks and so on, then you can go ahead and deploy it by sending it to the grid or some batch computing to process over a larger data set for you automatically. Similarly, if you are writing a document, you can imagine deployment being compiling a PDF and uploading it somewhere automatically for you to view, and so on. There are lots of different ways and different contexts in which CI/CD works, and if you have questions about it, feel free to ask me or any of the mentors. Now, at the end of the day, you can imagine this being sort of like a catch and release, almost like fishing, which is why I have a GIF here about it. And the idea here is that you want to be able to catch exceptions, but if there are no exceptions to catch, then you can go ahead and release the code in the wild, which is a little bit different than fishing in a way. So, imagine that the CI needs to be able to catch these break-in changes, but this is a little bit tricky because you can imagine that perhaps your first instinct is to parse the log file and look for errors or warnings. But how do you know that every tool that you use is going to be outputting errors or warnings in the same way? How do you even know that the tool you're using is going to print out an error or warning in the first place? There has to be a mechanism in place for the CI job in order to catch these changes that break. Similarly, let's say that you want to be able to check it with some other code like, C++ versus LaTeX versus Python. There has to be a way to do it consistently. We'll talk about that in the next session. At the end of the day, the whole idea is to automate your entire workflow. Anything that you can run on your computer can be equivalently run in a CI job. There could be a little bit of extra work that needs to do to make this happen, to make it more CI friendly, but it's definitely worth it because it pays off in the long run by saving you time and having to rerun all of these checks all the time by making your computer do it. So, as I mentioned before, CI/CD isn't just for analysis code, but it can be for anything that you can think of. Anything that you want to be able to automate. Let's say you're a convener or sub-convener, or you're sharing some group, and you need to maintain some documentation about the group, such as the status of meetings or links to various things. You can imagine that you can build up a repository that stores data about all this information and automatically update a page whenever you have new changes to make. You can imagine it this way, you can version control pretty much everything you like. And there are lots of different solutions, as I mentioned at the beginning of this video. We will generally encourage that we use the native GitLab CI CD solution, which is built into GitLab in general. Now, there are other solutions, such as, for example, if you are using GitHub. And then there's Travis, Circle, all the way down to CodeFresh. And I made this list in order of the CI/CD environments that I like the most to CI/CD environments that I like the least. So, for example, if you are using CodeFresh, please don't. I'm not going to help you debug that. So again, for today's lesson, we will only be focusing on GitLab solution. However, all the concepts that will be taught today, such as pipelines, stages, jobs, artifacts, dependencies, caching, they all exist in some way or form across all of these different solutions, perhaps by the same name or different names. So, for example, GitLab has two features known as caching and artifacts. Travis doesn't quite have the same functionality in place. However, they do have similar names, but you should be aware when you're translating from one CI solution to another, you should be aware of the differences amongst the two functionally. And again, if you have any questions about some of the more popular ones, feel free to ask me or any of your mentors. I'm sure we will be able to answer your question in some way or form. So that's it. Go ahead to the next section and we will start understanding about breaking changes. Now, in this video, we're going to be talking about exit codes. And if you remember from the previous video, we were talking about how do we understand that a CI system is able to catch breaking changes in the first place, because it can reasonably parse all of these log files. So in the exit code section that we have here, we're going to go ahead and talk about an exit code. The idea here is that every single script returns an exit code. Anything that you run always returns an exit code. So before we actually make our own script, let's go ahead and use some native bash commands. So I'm going to go ahead to my terminal here, which hopefully everybody can see. We'll go ahead and start by listing a non-existent file. You can see here that we have this error that it cannot access the file. There's no such file or directory. But how do we get this exit code for it, knowing that it was an error? Well, we can type this little helpful thing here, echo $? And you see here that I have the exit code 2, which indicates the failure. What happens on success? So, in order to get a success, we're just going to do an echo command. Echo whatever. And then get the exit code for that. So you can see here that the exit code 0 implies success. But, so, this works for anything. So you can imagine, for example, what happens if I typoed a command such as get status, and I typed in get status instead. You can see that this failed because Git doesn't understand what we're trying to do, which is reasonable because we can't spell. You can see that the exit code that it returned was 1. So this works in a very generic fashion. So you might notice at this point, interestingly enough, you would expect perhaps the execute of 0 means failure and that an execute of 1 is true, success, because you might expect it to be a Boolean output, where 1 is true and 0 is false. However, this is not always the case, and what you want to think of instead is to ask yourself the question, was there an error in executing the command? 0 means no. Anything other than 0 means yes. And execodes have different values which allow you to look it up in the manual to understand what that value refers to. Let's go ahead and talk about Python. Alright, since everybody's familiar with Python, and so we're going to go ahead and open up the Python interpreter, which I'm doing right now by typing in Python. I'm going to go ahead and import OS and subprocess. Now, we're going to go ahead and do this ls command again, but we're going to go ahead and try and figure out how we get the execute from Python. So if I go ahead and type in os.system ls like so, you can see it prints something. I'm going to go ahead and do os.wexit status on the return value. And you see that it returns 0, which is great. So now we're able to get the execute from this. Let's go ahead and take in that same command again, but this time for a non-existent file. So you can see here it prints out to the screen, but let's see what the return status code is, and it's a 1. So this is great. And this allows us to do exactly what we want from Python to access the status code. To access the execute. Now, let's go ahead and talk about actually studying these executes in the first place, because at the end of the day, you're going to need to learn how to write your own scripts and make sure that those scripts execute correctly with the right execute. So, the first thing we're going to do, we're going to go ahead and exit out of Python, and we're going to go ahead and create a file. And we're going to create a file called bashexit.sh. In this case, I'll touch it, and then go ahead and edit it with your favorite editor. I tend to prefer Vim. So I'm going to go ahead and type in everything that we need here, but feel free to copy paste. So what I'm doing right now is just using native bash commands that allow me to put in any execute I want by using what's called exit0 or exit59. And the idea behind this bash script that I'm making is that if I feed in anything other than hello as an input, it's going to give me a non-successful execute of 59. So, assuming that you have this all typed in, we're going to go ahead, save it, and quit. And I'm going to go ahead and make that file executable. chmod plus x, and then let's try running it. Bash exit hello. We get an execute of 0. Now let's try goodbye, and we get an execute of 59. Notice how in this case we didn't actually print anything to the screen. So don't always expect that there be a log entry or something printed out to the screen whenever something succeeds or fails. You always want to rely on executes. However, just doing this in Bash is probably not as enlightening as being able to do it in Python, since Python is definitely a popular language of choice. So let's go ahead and make this exact same script, but in Python. So similar to before, touch bash exit.py, python exit.py. I'm going to go ahead and edit it, and again, something similar. We're going to go ahead and import sys, and sys will allow us to get the command line arguments that we pass in to the Python script. You can see on my left side how similar the bash and the Python scripts are here. and that's actually meant to be on purpose. We're mostly just trying to highlight to you how very straightforward it is. Now I've gone ahead and exited, and I've made this executable so I can run this from the command line as well. And now we're going to go ahead and do the exact same that we did with the bash script. We're going to do hello, and we get an execute of 0. We're going to go ahead and do goodbye, and we get the execute of 59. And there you go. And now you can see how the bash script and the Python script look very similar. Now, the very last thing that we want to do to close up this section is to understand about how to ignore execodes. This is unfortunate, but sometimes it needs to happen because you encounter a script that decides to always give you an incorrect execode even though it may have succeeded or failed. And this is kind of unfortunate, and there's not so much you can do about it if you're not the one who created the script and you don't have a way to patch it to make it work. In this case, what you might want to do in the CI is be able to ignore the failure. So, what I have here is a very nice command that allows you to create an exit 1. So let's go ahead and just run this command without anything first. So you can see that if I run this command like so, and get the status code, I get a status code of 1. Now make sure you type this correctly because this is a little bit of bash wizardry and you might get yourself into an accidental fork bomb. But I would suggest you copy and paste it from the tutorial page. Now, what we're going to go ahead and do here is to ignore the execute of 1 and make it look like a success. We'll go back to the command. We're going to add in an OR. And this is a Boolean OR operator. And what this does is, if the first command in this fails, it's going to execute the second command for us. And remember that echo is special because echo will always succeed for the most part. There's very rare instances where echo fails, but in general it will succeed. And you can see here that it echoes ignore failure. And if I get the execute for this, I get an execute of 0. Now, let's go ahead and apply this to the Python script that we made before. So we have this Python exit, and remember that Python exit goodbye did an execute of 59. We're going to go ahead and do an ignore on that. And now we get an execute of 0. So, again, this is not really a hack in such a way to override these execodes, but it's not something we generally recommend you do. If you understand exactly what's happening and you feel justified to use this, go ahead and use this. But for the most part, this really should not be happening. But we provide this example here just so that you know that something like this exists for you to use if your CI jobs are unable to succeed. Anyway, that's it for the execute section. Tune in for the next section. So in this part, we're going to be talking a little bit about YAML, which stands for yet another markup language. Now, in this part, we're not going to be using the terminal at all, but I keep it on the side here just so that we can have consistency between all the videos that I have. So, YAML is a markup language that allows you to do pretty much anything that needs configuration. Is a plain text human readable data serialization language, and generally it's meant to be used by applications who need configuration files. In this particular case, or at least in the relevant context you might imagine, this is used for GitLab CI CD system, and we're going to go ahead and start using this as well for the configuration. Now, one thing that I want to mention is that in the debate between tabs and spaces, I generally suggest that you use spaces for your YAML document. Indentation in a YAML document is usually done with 1 or 2 spaces, but 2 spaces tends to be the unofficial standard that's commonly used. It's also okay to use 4 spaces, but definitely do not do 3 spaces. Alright, so as I mentioned, there's not going to be a lot of exercise, but I'm just going to go ahead and scroll through this web browser page that I have here for the tutorial and just talk about some of the common concepts that we see in the YAML document. The first thing that you see here are what we call scalars. Now scalars can be anything from a number value such as 42, floating points, booleans, all the way down to hexadecimal, infinity, null, plain text strings, date times, and dates. All of these are what we call scalars because it's more or less a single value non-complex object, such as a list or a dictionary, which we'll see shortly. And all of these scalars, however, are defined by what we call a key value pair. A key value pair is denoted by having this colon separated. This colon is special because you have to remember that YAML treats colon especially if you do need to have a colon in your string, such as, for example, a key, which I have on the right side in the terminal. You will need to wrap it in quotes. This will be the only way that YAML will understand this as valid YAML and will not get confused. Now let's go ahead to more complex objects such as lists and dictionaries. So as you can see here, we have a list of different Jedi such as Yoda, Qui-Gon Jinn, Obi-Wan, and Luke. So these are all the different Jedi that you can have as a list. The list is denoted by having a dash here. A dictionary, on the other hand, is where you have a set of key value pairs under that key. Similarly, since YAML itself is a superset of JSON, you can also write JSON style maps and sequences in the same way. For example, we can have a list as an inline list using brackets and commas, instead of having a list on new lines with dashes. And again, we can have dictionaries as you might expect them in Python or JavaScript using curly braces, instead of having this multi-level thing here that you have. Again, either way is up to you. Both of these are valid YAML examples. Now, the next part of YAML is going to be a trickier part, and it's going to be very important to understand, especially when we need to write script configurations for our CI jobs. And these are multi-line strings. However, what we're going to do instead is go to this little page that I have linked here, which is called YAML-multiline.info. And I find this page very useful to understand how multi-line strings work. And this is where instead of having a string on a single line, you want to have it on multiple lines. And there are lots of different ways to do it. So what we're going to show you here, hopefully you can see this demo that I'm highlighting. I'm going to scroll just so that you can understand. There are different ways to denote a multi-line string depending on what you want the behavior of YAML to be. So this top piece here is the YAML definition that we have. These /n's are going to be the explicit new line characters that we have. And then this bottom piece here with the result will show you what the parsed YAML result will look like. So let's look at this YAML definition. The first one we have here to denote a multi-line string is with a caret. And what this caret does is it determines that we want to have a single new line at the end, so it chunks. Now, all of these new lines that we have here are replaced with spaces, so it's folded. Let's say, for example, we choose to keep the new lines in, where we use a vertical bar instead. You can see now that the new lines are included literally in between the blank line here. However, you'll notice that all of these new lines at the end have been chomped away. This chomping is done by default in YAML. It's called clipping or chomping, depending on what you want to do. Let's say you definitely do not want a new line at the end. You put a dash after, depending on whether you want to remove all extra new lines or not. The dash will still be there. That dash is to strip the new line from the end. Now, let's say you want to keep all new lines. Then you need to use the plus. Hopefully this makes sense, but you can go ahead and play around with this website more to understand all the different variations of how to do multi-line strings. I'm going to go back to the tutorial here. The main reason that I have this is just to highlight that multi-line strings can be handled in many different ways depending on what you want to do. What I have in the tutorial here is a way of how you might want to do this for the scripts that you're writing. You can see here that we're going to remove the new lines and replace them with spaces, and then remove the new line at the end with this dash here. And so you can see an example of how the script is folding it correctly by taking these echo foo, echo bar, echo bash, which are new lines in YAML, and we'll convert this into a single line by replacing the new lines with strings. And because of this dash, it will strip the new line from the end. Alright, that's it for multi-line strings. Let's go ahead and talk about nested objects. Now remember that above with the Jedi that we were showing here, we can have a single level list or a single level dictionary. But what if you want a list of dictionary, or a dictionary whose key value pairs are list valued instead? So there are different ways that we can do nesting. So for example, we can have a nest here where request itself is just a list, which is fine. However, what we can do instead, you can see, is we can additionally have the second item here be a dictionary. Now you can see that request itself is a list by these dashes here. The first element in this list will just be a string, but the second element in this list will be a dictionary. And as long as you do the spacing correctly, YAML will understand this as a nested structure view, and this is sort of the powerful feature of it. Now for the last two things we want to talk about are comments and anchors. Now comments in YAML are just a pound sign. Now remember, like the colon, whenever you use the pound sign and you want to use it explicitly in your value, you need to put quotes around this. If we go back to the terminal, here's an example again. This will tell YAML to treat the to treat the pound literally instead of an actual interpreting it as a comment. Finally, to close up this section, there's a handy feature in YAML which are called anchors, which allow you to duplicate content across your document. And you can go ahead and look at this tutorial on how these anchors are being done here. But anchors are sort of like references in C and C++, which allow you to dereference an anchor which injects backcode into the YAML document depending on how you anchor it. So for example, this is how an anchor looks like here. We use the ampersand name of the anchor, and then we can dereference it using the asterisk to dereference. It really looks a lot like pointers in C++ and dereferencing pointers in C++. So as an example, let's say we want to anchor this dictionary called base, where base has a key called name. Everyone has same name. We're going to go ahead and create an anchor called ampersand base, so the anchor itself is called base. Then we're going to create another dictionary foo. We're going to anchor that as well. But then we're going to go ahead and inject all of the keys from base into foo. And this means that foo will have a name key, everyone has the same name, and an age key of 10. And then similarly, you can do the same thing for bar here, where now both foo and bar have the same name, but different ages. And this allows you to do sort of repetitive coding or duplicated content without explicitly copying values across your YAML document. And so that's the end of the YAML section. Tune in for understanding how we use YAML with CI CD. Alright, welcome back to the CI CD tutorial. So, in the previous section, we learned a little bit about YAML, yet another markup language, and how it's used as a generic plain text, human readable, computer friendly format that allows you to configure anything. What we want to do in this particular video is talk about how it applies to GitLab CI CD. So we're going to go ahead and open up the YAML and CI thing that we have here. So let's take a look at an example of what the GitLab CI YAML looks like. This is going to be one of those very short videos that doesn't have any particular exercise using the terminal. So what we're going to do now is go over what these YAML examples look like for the GitLab CI. So what we have here is an example configuration. So let's go ahead and read this. We're specifying a key called image. It has a value which is a string called /gcc make. We'll talk more about the context or details of what that means later. The next key that we have here is the before script. This key happens to be a list of strings such as make directory build, and in this case it's specifying a list of commands that will be executed before the actual script runs. Then the next thing that we have here is a key called build code. This key has a value which is a dictionary pointing to a list here. In this case we have a script which points to cd build, cmake source, and then cmake build. Now one little thing that I want to highlight is that in GitLab CI YAML, script commands are a little bit special. Sometimes, as we mentioned already in the YAML section, there are commands that need to be wrapped in single or double quotes. Sometimes commands will contain a colon that needs to be wrapped in quotes so that the YAML parser knows how to interpret the whole thing as a string, as I mentioned before. There are also some other special characters that you need to be aware of. When in doubt, try to wrap this either in a multi-line string or use quotes to ensure that the YAML will parse it correctly. At the end of the day, this entire structure that we have here is relatively simple and human readable, which is why YAML is used for CI configuration. In this particular case, what is this YAML seeing with this configuration that we just looked at? So this configuration is using cmake and make. It defines a single job called build code. That job has an arbitrary job name, and there are different commands that can be executed in it. Before any script that is being done, we have a before script, which is aptly named before script. And that's it. That's entirely what this job is doing. It also runs this entire job in a Docker image which it pulls from Docker Hub. This is /gcc make. So now that we've got an idea of what an example file looks like, let's just talk a little bit about the overall structure. So you can see here that we're going to define 3 different jobs. We're not going to talk about the parameters of those jobs yet, but we're just going to talk about how this YAML file is generally structured. What we do is we specify jobs by particular names. These names are generally arbitrary. However, there are particular names you are not allowed to use, which you see in this list below, such as default, image, services, stages, type, before script, after script, variables, and cache. These are names that your jobs cannot have, because these are already used by other top-level configurations for the GitLab CI. By default, all of these jobs that you run at the top level will run in parallel. If you want to run them in serial or a mix of parallel and serial and so on in some sort of complex directed acyclic graph structure and so on, we'll cover this later in a different section. For now, we're going to talk about jobs running in parallel, but we'll get to the point where we can start doing things in serial and parallel. So, let's go ahead and look at some of these global names that we have here. So if we took that previous CI example, we can add in another global name called stages. And we can define stages as a list of 3 strings: build, test, deploy. We will get to stages in a later section of this tutorial. The other thing that I want to mention is that when I refer to particular variables, because I like to use the GitLab CI convention, we use a colon to denote the scope. So, for example, if I want to refer to the image of job 2, I can say job 2 image. And this overrides the image at the top level, which I refer to as :image, where a prefix colon here means the root level of the YAML file. Jobs can also have various parameters. There are a ton of parameters that jobs can have. You've already seen one so far, which is called script. However, there's a lot more. So if we click the configuration parameters of the GitLab CI docs, which contains a lot, you can see all of these different parameters that jobs can have. Each of these are clickable, so you can go ahead and click on a parameter to see it in the documentation. Let's go ahead and check out script for an example. You can see the script being used and an example of how it's used in the documentation. You can see that GitLab CI docs wrap it in double quotes just to be safe, but they also mention that there are lots of different things that you can do with it, such as a single value or a list of values. And they show you lots of different things that you can do. You can see, for an example, GitLab CI YAML has an example of that extra code in order to prevent it from failing, for example. This is the example of it. Anyway, these documentations exist for you to go through on your own time. We're not going to go through them explicitly. Hopefully, you should be able to understand how to use this reference. And next, we're actually going to go ahead and start our exercise by writing our first GitLab CI YAML file. So tune in next time. In this video, we're going to talk about starting up with our very first GitLab CI job. And this is what I call the hello world example, where we're just going to get a random computer somewhere to tell us hello world in the log file of our repository. So, let's go ahead and open that up. Now, we're going to go ahead and add CI CD to a project. And I've got my terminal on the right side here, which is already in the virtual pipelines event selection repository with all of this code in here by default. So the first thing we're going to do is we're going to go ahead to our repository that we made in the GitLab. I already have this open in another tab. So the first thing we want to do is actually go ahead and add GitLab CI YAML. So let's go ahead and look at this code block that we have here on the left. We're going to go ahead and echo hello world straight into a brand new file that doesn't exist yet, as you can see from the list above. So we're going to go ahead and create that. Now, let's go ahead and create a new branch, a feature branch, for adding the CI to our project. The git checkout -b means to create a new branch. And we're going to call this feature/add CI, this feature being what we call a feature branch, and it is a sort of a human-friendly way to denote the purpose of this branch. So we're going to go ahead and add the GitLab CI YAML file that we just made, and go ahead and commit it. And then push it up to our repository. The -u here means to set the upstream branch, so that means that the branch that we have locally will be tracked by the new branch that we create on the remote. And you can see this very last line here, branch feature add CI set up to track remote branch feature add CI from origin. So that's what the -u flag did. Alright, so let's go ahead back to the repository, our project here in GitLab, and let's go ahead and get that new branch. Here it is. Let's navigate to it. And already you can see that we have this Redux here at the top. So the pipeline failed. Well, that's both good news and bad news. The good news is you managed to make a pipeline happen. The bad news is it failed. So let's go ahead and check it out. And you can see that the error here in this very nice red box is that it said the included GitLab CI YAML doesn't have valid YAML syntax. That makes sense. Alright, we're going to go ahead and fix this. So you can also see these little tags here that I'll highlight over. It tells me that it's the latest pipeline for the most recent commit on this branch. The YAML is invalid, and there's a CI CD YAML configuration error. Fantastic. So that's just a little thing that we have here for the linter. So let's go ahead and click on that. And let's go ahead and add in the contents of the GitLab CI YAML file, which was just hello world, and click validate. Now you can see here that the linter has mentioned the syntax is incorrect. Great. So what a linter is it is a tool that knows the context of what you want to validate or check the format of. So imagine that YAML is some sort of structured language that is associated with a schema. We know what a correctly structured YAML looks like. So all we do is we have a tool, a linter, which checks the file that you create against the expected structure of any YAML file. And if it finds an error, it lets us know. This way, we can use the linter to figure out how to write a YAML file that doesn't crash. So we want to make this hello world actually work. So let's go ahead and actually add a script. When we have a script called echo hello world, we can do it this way with quotes around it. We can also, actually, let's go ahead with quotes around this for the most part. Let's look at the tutorial page to double check what I did here. Yeah, we'll get to this merge request in a second. So let's go ahead and try to validate this YAML file that we have here. And now the linter says that this is correct. It says here that we create a test job called hello world, which is at this top line here, which is great. And it tells us what the value of the script is. Alright, let's go ahead and get this working. So we're going to go ahead on the terminal and fix this up. Let's add the changes that we have. Mention that we're fixing it. And let's push it. Alright. Now I'm going to go back to the project. I'll just go back in my browser. Back a couple more times. Great, back to the pipeline. Alright, so let's go back to this branch that we have here. The next thing I want to do is create a merge request. And to explain why I want to create a merge request is so that we can keep track of all the pipelines that have happened for this particular branch. It makes it just a little bit easier to keep track of. So we're going to click that green button here. We're going to start this as a work in progress. We're going to call this feature add CI to project. Exclamation mark, because we're very excited about this. And go ahead and click to submit the merge request. So now that we've submitted the merge request, you can see that there's 4 separate tabs here. So this pipeline tab is the important tab that I want to point out. This tab allows you to see all the pipeline that have run for that particular branch. And this is a nice thing to have, so that means whenever I submit new commit, I can go back and look at this tab and see the most recent pipeline. So, I've just noticed that this pipeline has passed, and our hello world has passed, so let's go ahead and click on it and see the output of that job. There's a whole bunch of output here. I'm just going to look all the way towards the bottom, where I see these 2 lines. Line 29 here is the script we're executing, echo hello world, and line 30 is the output. Remember that the exit code of an echo command is 0, therefore this passes, and the CI marks this as a succeeded job. And this is great. And this is our entirety of the hello world. Just scrolling through to double check. Alright. Let's talk about this last part of this section before we move on. So, I mentioned 2 little keywords here, pipelines and jobs. So you might be wondering, what's the difference between pipelines and jobs? Well, if you go back over this tab here, you can see that this pipeline has a single job called test. A single job called hello world and a test stage. So right now, it's not very clear what the separation is until we do a much more complicated setup. But you can see that in this particular merge request and in this particular branch, we have run the pipelines twice. The very first pipeline here has failed with an invalid YAML, and the second pipeline has succeeded. Hopefully that makes more sense. There are also stages, but we're going to go ahead and talk about stages in a future task. You can imagine stages as being a way to group all these different jobs, and pipelines is a way to group both stages and jobs. But to summarize, in order to get CI running in any project, all you need to do is add a .gitlab CI.yaml file. And CI linters are very important to do. So that's the end for this section. Join us next time as we start adding more features to the CI. So in the CI/CD tutorial, we just recently finished adding a hello world job and ran a successful pipeline, as well as set up a new feature branch and set up a merge request and mark that as work in progress. So we're going to go ahead to the next part and actually add CI to the existing code that we have. So I clicked on the page to go ahead, but let's remind ourselves of what files we have here. Now I'm really going to care about what we have, the skim.cxx file. This is a C++ file that needs to be compiled. Now we could do something where we pre-compile it and add this binary to the project, but then that adds a lot of extra space that we have to keep copying over every time we clone, and it adds extra bloat to the repository. We want to try to keep things as sleek as possible so that things clone fast and it's easier to work with. Additionally, because compile binaries work in very specific architecture, the architecture you compile for, it's not guaranteed that whatever we compile on our computer will work in the CI. So we should get this compiling in the CI. So if we scroll down a little bit, you can see these two lines here of what seems to be working on my computer in order to get things to compile. So we're going to go ahead and add a new job in our GitLab CI YAML that's going to run in parallel to this hello world job that we have. And it's going to go ahead and compile the skim.cxx file that exists. So let's go ahead and add a build skim job here. And we'll do a script, and we're going to go ahead and do a list. So we're going to set the compiler variable, and we'll go ahead and run the root config command line interface that comes when you install root, and that will tell us what the CXX flag, the CXX compiler that root used is. We're going to go ahead and grab that environment variable, and we're going to go ahead and add in these extra flags here. I believe that's a 03, and then, that's an 03, and then wall, extra, WP, Dantic, skim.cxx. You can go ahead and copy paste. I just choose to type in to practice my typing skills. So let's go ahead and add this new job in. We'll go ahead and save this file. And we'll commit it. Let's call this build skim binary. Let's go ahead and push it. So, I mean, this works on my computer, so it should be working in the CI as well. So let's actually go ahead and check this. So we still have this, and we see that it just pops up here as a new pipeline. So if I click on this, we have this build skim job, so I'm going to go ahead and look at it. And, interesting. So root config doesn't exist. And so that's the problem, because it seems to be that root isn't available. So if I go ahead and look up here, we can see that the Docker image being used is right here. It's using a default Docker image called CI tool/CI worker for CERN CentOS 7, if you can see it at the top. So I guess that default image doesn't have root, which isn't all that useful for us. So obviously we want to be able to compile the skimming code with an image that has root. So let me go back to the tutorial to remind myself of which image that we need to use. And right here, root project root conda. Alright, so we're gonna go ahead and use that. Sorry, that's root project / root conda. So let's go back in here, and we're gonna go ahead and add in an image to this job. Root project root conda 6.18.04. We're adding this image here. Use root image for build skim, and we'll go ahead and push that. Alright, so I'm going to go back to my merge request that I have here, and we should see the new pipeline. Maybe I need to refresh. There it is. So let's go back and look at this build skim again. And it's running, so let's see what happens when it runs. Now hopefully everything should work, because I think root config generally just meant that we needed an image that already has root pre-installed. So right now there's a little bit of time that needs to happen in order to pull the Docker image root project / root conda. One thing to point out while this is being pulled, the Docker images for root will always be a little bit larger than some of the other Docker images you work with. That's because root is in general a heavy / bladed dependency. So we're going to go ahead and wait for this Docker image to pull. Let me look ahead and see what's next here. It looks like we expect it to fail, so let's see what happens when it fails. Alright, interesting. So it looks like it's failing because there's this error here with the fatal error root/dataframe.hxx. It seems to be that there's no such file or directory with the include. That's interesting. So it looks like we're missing some include flags here. So let's remind ourselves for a second, perhaps this has something to do with root config. So let's see if we can remind ourselves of what happens here with the root config for a second, because obviously we must be missing some linked binaries here, or some linked header files in order to compile it correctly. So let me see. Let me remind myself what we need to do. So my guess is if it fails that way, we probably need to add compiler flags. Let's see if I forgot that in here. Indeed. So that's one thing that's a little bit different on my computer. My computer already has root set up to add in the compiler flags by default. So let's go ahead and add in another line at the end here for the flags. And if I remember the root config command correctly, it should be cflags and the libs. That looks right. So let's go ahead and add that in to the end. So let's go ahead and do let's add the flags at the end, shall we? Or at the beginning? I don't know. I think for clarity, let's just add the flags at the end to indicate that these are the compiler flags. So now we've added this line here for the flags, and we've added the flags here. Let's go ahead and see if this works. We'll add that file, add the changes, we'll commit them, and then we go ahead and push them. Alright, so let's go back and look at the merge request again, and I guess we need to refresh. Alright, hopefully this should work, and additionally, because we pulled this image previously, hopefully the root project image has been cached and we're using a similar runner. But it looks like this may not be the case, but that's okay, we'll just wait another minute here. In the meantime, while this is running, let's go ahead and talk about this new feature. So, right now, if we looked at this GitLab CI YAML file, we built this for a single root version 6.18.04, but perhaps we want to also build this for other root versions. So, if I go, I'm just going to go and do this in the browser just so you understand. But this is the root project. So this is the root conda image under the root project. And I see that it has a couple of tags here. This 6.20, 6.1804, which is the last one we're using. But there's also latest. Interesting. So perhaps we should build it for a specific version that we care about. But maybe we want to also build it for latest. Okay, so it looks like it's running and the job succeeded. Great. So let's go ahead and do a build skim for latest. So I'm going to copy all of these lines and then create a new job called build skim latest. This image that I'm using here, where the version tag is 6.18.04, I'm going to replace it with latest. But I'm going to keep everything else the same. Now, because these jobs are listed at the top level, they will all run in parallel by default. That means we'll build the skim for 6.18.04 at the same time as we build the skim for the latest Docker image. However, one thing that we may not care about, such as this for this latest, we don't necessarily care if our code compiles on the latest version of root. You can think of this more like a canary. So what we care more about is knowing that it builds on the latest, but if it doesn't, we shouldn't fail our CI because of that. So we're going to go ahead and add one last thing in here called allow failure. I'm going to put yes, which means I allow this job to fail. It's okay if it fails. I just wanted to tell me if it fails. Therefore, it doesn't actually crash the entire CI. Alright, so let's just go ahead and add this in. Add build skim latest and allow it to fail. Now if I go back into my browser, I'll refresh again, and there it is. Now I generally will expect this to succeed, but because I haven't touched anything about build skim, I know it's reproducible and it will pass. So let's go ahead back to the tutorial and see what else we should do here. So we've done the building multiple versions. And this last thing here is perhaps we want to use a before script, because we are setting some environment variable flags that aren't necessarily part of the script. I guess this makes sense, so let's go ahead and back to our GitLab CI YAML file and fix that up a bit. We'll add a before here, adding the script there, adding the before here, and adding the script there. And we can go ahead and clean this up. So once I make all of these changes, I'll stage it, clean up YAML a little bit, and then push those changes. Alright, so at this point, there's not much else left for this section, so let's go ahead back to the pipeline. So it looks like the build scheme and the build scheme latest passed for the previous thing we just did, which is to add the build scheme latest. And now the cleaning up the YAML a little bit should also work. Let's just peek into build scheme just to be sure that things worked as we expected to. So while this is pulling, I guess, from the cache, or maybe it's just pulling from Docker Hub, one thing I want to mention that's at the end of this tutorial section is about changes. So perhaps you might run only particular jobs in your code to only run particular jobs in your YAML to only run when specific files have changed. So in this case, you can imagine build scheme only ever needs to be rerun when scheme.cxx changes. And therefore, it builds a new .scheme only if this file changes, so if you change some other file and not this file, it won't build it. However, this isn't something that we're going to do as part of the tutorial, but it's just something for you to be a little bit aware of, and that should work pretty well. Alright, let's go back and see where we are. So the job succeeded, and we are done with this section. So we just recently finished up in our CI CD tutorial actually getting the scheme.cxx file to compile. And so that's this file here in the code that we have. So let's look back at our GitLab CI YAML file, and we already see that there seems to be some sort of duplication happening here. And it would be nice if there was a way to sort of not repeat ourselves too much. So let's go into the dry part of the tutorial, where dry stands for don't repeat yourself. So we want to be able to make job templates. So the nice thing about the GitLab CI is that we want to be able to define a job that doesn't run. And if that sounds a little bit weird, it kind of is, but you get used to it. So by default, you might expect that you want to create some sort of job template here. Let's say we call this build template, or build scheme template, whatever you like. And we try to create the template, and we put the before script. I'll just copy and paste this. Let's say we try to do something like this, but then we run it to not run. So you might think that we add in a comment before everything. Well, that doesn't make sense because it's a comment in YAML, and that means YAML will ignore it when parsing it, so the GitLab CI parser won't even see it in the first place. Instead, there is a workaround, or actually something that is supported natively, and that's when you prefix the job name with a period. So if we call this bit.build underscore template, this allows us to create what we call a template job. So if you scroll through the tutorial, our first thing that we want to do here is to refactor this code that we have in order to take advantage of this build template. So if we go ahead and do that, we're going to create this build template job. That's our first step. Alright, now obviously we can compile and push, and this should do absolutely nothing. So you know what, let's go ahead and do that. Add a build template job. We'll go ahead and push that. And go back to editing this file. And I'll go back to the merge request that we have here. Oh, sorry. It showed up, but I'll just see. Now you can see there's still 3 jobs defined here. Build scheme latest, and hello world, even though we have this build template. So it is a hidden job. That's fantastic. So now what we need to do is figure out a way to actually extend or copy this. Now we could have used YAML pointers for this. However, there's a different way to do it, and that's called extends. To understand how extends works, I have this example that I put in the tutorial here. So imagine we have a hidden job called only important, which contains only parameter with values master and stable, as well as a tags parameter with values production. We also have an in Docker hidden job, and that has a tag as well called with the value Docker and defines an image. Now imagine we have a job, an actual job called rspec. Rspec will extend from only important and in Docker, and then additionally adding a script. If you actually parse this YAML file, it will become the following code here. It will contain the only stuff from only important, master, and stable, but you'll notice here that it doesn't contain the production tag. It only contains the Docker tag. This is because while only important was defined first here, the Docker tag will override the previous tags defined here. Hopefully this makes sense when you look at it. So let's go ahead and use the same thing, but with our GitLab CI YAML here with extends. So I have this job template. So what I want to do is delete these lines on both of them. And let's go ahead and add in an extends parameter. And the extends parameter will contain the name of the job template, the hidden job, which is the build template. Let's do that for both of them. And hopefully once we refactor this code, have I deleted too much? I have. Sorry. We should also make sure we have the allow failure as well. So now that you can see we've refactored this code, and while it isn't a huge reduction in code that we've had before, you can see that we've now reduced things a lot. So that means that whenever we need to change something about the script, such as adding a flags variable because we forgot it, it will affect both the build scheme as well as the build scheme latest. Alright, let's go ahead and add these changes. Are these really changes I wanted to add? Yes, they are. That looks right. So let's go ahead and commit this. And so let's say we'll commit this as a dry our code up a bit. Capitalize dry because we don't want to repeat ourselves. We'll go ahead and push things. And let's go back here to our merge request and we should see a pop-up. So the previous one where we added the build template path as we expected it to. And now let's go ahead and see that this will run. And we will expect that this passes. And is there anything else in this section? Nope. So just to remind you of what we've actually done. Jobs that are prefixed with a period will become a hidden job in GitLab CI. They won't actually be run, but can still be referenced using extends or using anchors for everything that you want to do. And we can use job templates that allow us to stay dry and not repeat ourselves. We recently went ahead and tried to clean up our code to make it drier a little bit. If we go ahead and look back at what we just did, you can see we added this build template here, which is a hidden job, and then we went ahead and extended it. So let's go ahead and talk about stages, because clearly, if you look at this, we have this hello world stage, this hello world job, which isn't necessarily going to want to be in parallel with the build jobs that we have. So we want to group things a little bit more. So opening up the stage part. So looks like we started correctly. So to understand the reference, just remember that when we have a colon, that allows us to figure out what we talk about. So what I have here, we're going to talk about this global parameter called colon stages. and the extended per job parameter :job : stage. So this allows us to group up parallel jobs and allows us to just sort of start defining this directed acyclic graph, also called a DAG, D-A-G. So what we want to do though, however, is we want to, let's check out what that default stage name is, right? So you can see here, if we go back to the merge request, the pipelines tab, we can see that this check mark is part of the test stage. So it looks like if we don't specify a stage at all, the default stage that GitLab will choose is test. This test stage will have all of these jobs in it. So what we want to do instead is, let's see here. We want to define a greeting stage and a build stage. So we want to add a :stages variable all the way at the top. And we're going to define a greeting stage and a build stage. And what did I mention? The key will be under :job : stage. So that means that we can go ahead and update this hello world to be run in the greeting stage. And then we can also update the hidden job that we have here to be on the build stage. This will update the build skim and build skim later correctly. So let's go ahead and make those changes. Let's just double check that we've staged the right changes. Looks like there's only additions, which is good. And we're going to go ahead and do add stages. Greeting and build. Alright, so now that we've pushed things up, I'll just open this up again on the side so that we know what this looks like. I'm going to go back to the pipelines here in the merge request, and I see now that there's 2 circles instead of 1. So it looks like there's a test stage here, and now there's a greeting stage which only has hello world. And then there's a build stage which has the build skim job and the build skim latest job. Now, if I click this little square icon on the left or this pipeline here, both of these will open up the pipeline specifically. You can see that it actually shows this little graph here of the jobs and the stages at the same time to visualize what's happening. And this shows you that the greeting stage will run first before the build stage does. And once the hello world job has passed and the greeting stage has finished all of its jobs, then the build stage can go on, and we're starting to see that things pass. And hopefully this all makes sense and this is something that you've been able to get. And that's entirely it for this entire section. I will point out that if you look at the GitLab docs here, the GitLab docs have a nice thing about how all the stages work in terms of the parallel and serial execution if we want to know more details about how it actually works. But you just learned how to make some jobs run in parallel and some jobs run in serial. And stages allow you to help define these job dependencies, which we will explore more in a later section. Now we've gone ahead and split our jobs into stages. And we've defined 2 stages, a greeting stage and a build stage. It seems like the next thing we should do is start thinking about our entire pipeline, our entire chain. And so what we want to do is start actually skimming, doing something with this thing that we've compiled, the skim.cxx. So let's go on to the next step, our skimmer rigs. So we're going to go ahead and just be a little bit naive. So I know we need to do 2 things. I know we need to add a run stage. So if I go to the GitLab YAML file, we'll add a run stage. And in this run stage, we're going to go ahead and add in a skim ggh job. I think for now, I just want to be able to run this skim binary that we created from build skim. So, let's try this now. Alright, so let's see what happens if we just run this. Add skim GGH job to run stage. And we run this. And we should see the pipeline update, but I'll refresh. There we go. We've got our 3 stages. So, let's go ahead and let this run to double check that things work. I already know that this is going to fail, by the way. But we should go ahead and look at this failing first, just so we understand how it fails. So we just have to wait a little bit. Maybe refresh. Let's peek on the previous jobs here. How's build skim doing? Build skim finished. So it looks like build skim latest was still running. And yeah, hold on, we're just taking a little bit of time to pull those Docker images. The Docker images are pretty bloated with these root installations. Alright, let's see here. Any second now. Any second. Come on. I guess I am a little bit impatient here. There we go. It uploaded the artifacts, which is great. So let's go ahead to the run stage. Let's see what happens. This should run pretty quickly. And there's the error. And okay, so there is no skim binary. So the problem here is that we're not pulling artifacts from the previous job. As you can see here, this downloading artifacts line, there's no artifacts being downloaded. So we probably need to set up artifacts. I will link you in the tutorial more about job artifacts. But by default, artifacts from all previous stages are passed in by default. But we should also define dependencies, because dependencies tell us which artifacts to pick up. I have a lot more information about what we can define with artifacts that you can read through on your own time, such as specifying the paths, the name, whether to use all untracked files or not, when to upload artifacts, when they expire. And there's also this weird thing for unit tests, which I've never really used before, so we're not really going to cover it in the scope of the tutorial. So let's go ahead and add these artifacts to save everything. So let's see how we do that. So looking at this GitLab YAML file, we're going to go ahead to this build template here, this hidden job, and I guess under the script, we're going to specify artifacts. We're going to specify the paths, the skim binary that's being created, and we want these to expire in 1 day. So that looks good. Now the last thing we need to do is we need to tell skim GGH to only get the artifacts from build skim and not build skim latest. So we need to define dependencies, or declare them. And we declare the build skim job as a dependency for skim GGH. Alright, so let's go ahead and do this. GitLab stage. And okay, this looks correct. Artifacts and dependencies. Alright, so this should hopefully run a little bit faster than the last time. Let's go back to the branch, which doesn't help. Let me find the merge request on the left and click that. There we go. Pipelines. Alright, so hopefully this runs a little bit faster. And I guess I have a little bit of time to talk about artifacts. So, you know, these artifacts are very useful. They can be pretty much anything you want. You can imagine, for example, if you realize that you've compiled something and you don't necessarily need the rest of your code in a downstream job, but you only need the compiled binary, then you don't actually need to clone the repository anymore at that point, and you can just start passing around artifacts. So you can start thinking about how to make these jobs run faster and faster and faster by being very picky about what you clone or don't clone. You can also think of artifacts as pretty much anything that you want to upload after all the jobs are done. Because if we go back to all these pipelines that you have here, you can't necessarily see it unless I make this bigger, but if I click on this, sorry, that's not what I wanted to click on. If I click on the pipeline, that was an accident. If I click on the pipeline here, let's see, there are no artifacts defined here just yet. So I should be waiting for the job that added artifacts and dependencies. So I just need this to, that's finished. So here you go. You can see this download button here that allows you to download artifacts for the individual job. This will be very useful. So let's go ahead and see, oh, that still failed. Alright, let's go ahead and check out what happened here. Shared libraries. Did we have root in this image too? No, we didn't. Okay, so the other problem here is that we forgot to use the same image that we used for the build job. Because in order to run a binary, you need to have the same shared libraries that you compile with. Alright, so I guess in the skim GGH, we just need to add in the same image that we want to use. So let me grab that here. Build skim. I'll copy it from build skim, and I'll add it after, I guess, dependencies. Alright. Use root image for skim GGH. Okay. So hopefully that should work now. I'm pretty confident that should work at this point. So while this is running in the meantime, let's go ahead and talk about actually using a root file to run this skim binary on. So let's see what I have in the tutorial. Now I should mention the tutorial was originally written specifically to CERN. So we are going to use, for pretty much anybody who does not have a CERN account, we are going to use the eos public.cern URL here. But so I should mention that there's a lot of different ways that we could be getting data into the CI. So we could wget the entire root file that we want to run on every time, we can go ahead and git commit that root binary into the repository, but again, we want to avoid repository bloat if we can. Or maybe we can make a smaller root file, but it's going to be a lot of work every single time. So what we like to use is perhaps XRDCP, but for root files, we generally tend to use what's called XRDCP, which allows you to use root's xroot protocol to effectively stream or download a file, especially root files in the long run. So, nicely enough, we have these data files on EOS in the public EOS space. And there's a lot of different ways that we can figure out how to map it correctly. But so, if I went ahead and used my XRDFS right now, I can see that in here we have a lot of different root files showing up in this space. So what I want to do is go ahead and pour an added xrootd path here to streaming this input file. So I'm going to go back in here because I know how this GIMP binary works because we looked at the previous tutorial videos on this. We're going to go ahead and specify the public path here, which is eos public.cern.ch. So first, we need to specify the root protocol, then eos public.cern.ch. Double slash, then we need to do, let's see here, this path, sorry, it's not a double slash, it's a regular slash, but we'll add in and copy this path here, eos, root eos, hig, tau, reduced. And then we're going to go ahead and grab the glue to H because that's the GGH that we want to use. And we also need to add in the extra information that we got from the previous tutorial, 467.0.0.1. Which you can see down here if I scroll over. I should have scrolled, sorry about that. Now you note that in this particular command, I'm using my particular EOS base from the awesome bootcamp where this tutorial was written for. But we're going to go ahead and use this EOS public path instead. Hopefully people can see this, pause the video and type it in, but it should just work for you. So we're going to go ahead and save this. Double check that we're adding the right. That looks right. Let's run on an actual root file and let's push that. Alright, so we can see here, interesting, this root image failed. So we can go ahead and see how that failed. So it looks like what we did in the previous time is that it needs an input file, an output file, which we forgot to put, the cross section, the integrated luminosity, and the scale. So let's go back and look at this YAML file that we have here. We specified this input, but whoops, it looks like we forgot, maybe I forgot to specify the output here. Because did I put that in the tutorial? Yep, I did. So this is just Jordan being an idiot. Alright. So we're gonna go ahead and add that back in. Specify output root file. And push that. And hopefully that should work. So let's double check that this is added correctly. Alright, so this pipeline here, this second one in the list, will probably fail because we didn't specify the output file. So I'm hoping for this first pipeline on the list here to succeed. While we let that run, let's go ahead and talk about how many events we want to run over. So for CI jobs, at least at CERN, we use the concept of shared runners. So everybody has some sort of notion of shared computing time. For the most part, CI jobs can run at most an hour because that's a limit set by the CERN information technology staff. However, I generally like a particular job to run in, no more than 5 to 10 minutes probably. Fast turnaround time is much better and it's much easier for you in terms of development. You want to be able to get yourself a cup of tea or a cup of coffee out and then come back and see that the jobs are finished, and allows you to sort of reiterate and constantly develop. And because for some of you, because you're using the EOS public, you will not be getting an error, hopefully. But let's see what happens if we use the EOS public right now. And it looks like the build stage is still going on. So, as I mentioned, for the number of events, it really depends on the analysis. Some analyses can process 100 events a second. Some can do 1 event a second, especially when you're doing event generation, which could be maybe an event a minute, which could be very slow. I like to say that you want to process enough events such that your CI job are meaningful. It doesn't really make sense if you have an analysis that has a 1% selection efficiency and you only run 100 events, because that's not going to give you enough statistics to figure out if there have been physics changes. So you want to have perhaps maybe 10,000 events in that particular case. But let's say you have a job that has a, 50 to 70% efficiency, then you could do with less statistics at the end of the day. Alright, so where are we with the skimming? Okay, looks like the skimming is running, so let's peek in and see what that one is doing. So let's pull in the Docker image in now. So hopefully we should see it passing, or maybe it'll fail with some sort of permissions error. And look, it says it's processing the input, which is great. And there's 47,696 events in there. And it looks like it ran. Great. So there's not much more that we need to do. For those of you following the tutorial and you run into the permissions error, this won't be covered in the tutorial videos maybe. However, for those of you running on EOS public, you can proceed to skip to the next video of what to do next. However, for those of you getting the permissions error, you should go on to the next video and we can talk a little bit about variables. For those of you who want to learn a little bit more about variables, go ahead to the next video as well. If you're listening to this video, you ran into some sort of permissions error and you want to learn about how to add variables into your GitLab CI job in order to set up permissions. So we want to learn about how to give the CI job private information, but we don't want to give it to everybody else. So we don't want to put this into the YAML file. So let's go ahead and get into the spy game section. So if you were getting an error like this, for example, where you see server responded with an error, and that's because your file isn't publicly accessible, we need to give the CI CD access to our data. This is a good thing and it makes it easier to work with. So let's go ahead and get this working. So what I'm going to do now is talk about access control. So the access control is done by, what we're going to do is base64 encode our password and encode our password. And we want to base64 encode it because we want to make sure that special characters are passed in right when dealing with this complex backend that GitLab CI runs on. So as you can see here, I have this little line here that effectively will echo out the service pass. It'll pass it through base64 to decode it and then pass it into Kerberos init so that we can initialize the certain user with the correct password and get a Kerberos token to access files from EOS or some non-public area. So there are lots of different ways that you can run this locally as well, but we're going to go ahead and set things up. So, I have a lot of links here in the tutorial about how to set up a service account and how to make a service account. I generally suggest, if you are concerned, to make a service account, because this allows you to create an account separate from you, so that way if your service account credentials are compromised, you simply need to block the services. You need to deactivate or block the service account from access rather than your own account, which is going to be a little bit harder to get back. So there are lots of different ways you can define variables here. There are two main ways really are predefined variables as well as custom variables. So predefined variables is something that GitLab CI provides for you by default. If I click this link here to look at the predefined variables, you can see that there's a lot of these variables set up for you by default. A lot of them are prefixed with the CI underscore, meaning the continuous integration is solved. And as you can see, there's a lot of different ones, and we're not going to go over every single one. And in fact, we don't want to use a predefined variable. What we want to do instead is set up a custom variable. So I'm going to go back to my project here. On the left hand side, I have settings for CI CD, which is under the gear. So I'll go ahead and click on that. And under CI CD, we can expand to see these variables. So we can go ahead and add a variable in. So the first variable that I want to add in here is going to be the CERN user. And in this case, I'm just going to go ahead and put in my user account. Whoops, CERN user gstart. And this will be a variable. For now, we can choose to protect the variable, meaning on protected branches and tags only. For the purposes of this exercise, it's okay, we don't need to do that. And let's go ahead and click mask variable, but you can see we don't really need to mask the username because everybody knows it. Anyway, it wouldn't let me mask it because it needs to meet regular expressions. And it says here, it must consist of characters from base 64, must be a single line, must be 8 characters long. So I have a very short username, unfortunately, so that won't work. So let's go ahead back in and just do this again for real. Gstart, and let's add that variable. So you can go ahead and see that I added it in here as well. I can click reveal values just because I know that's a safe value. Now the next variable that we need to add in here is to add the service password. So I'm not actually going to do it on here. I'm going to go ahead and do it on a separate screen. And I'm going to go ahead and do we're going to create the service password. And the way I would do this is by doing something like this. Hunter42 base 64. And this will give me a base 64 variable that encodes it. So I'm going to go ahead and do the same thing here. So we're going to create this. I will mask it and then add it. And we're good to go. Alright, so now that everything's masked, we're going to go ahead and say, since everything's already saved, we're going to go ahead to the, where is it, pipelines. So we're going to go back to that merge request, back to the pipelines, and a pipeline that had failed, we can go ahead and click to retry it. If I expand the window out a little bit more, it's not there. Anyway, some of these pipelines, you can see, have a retry button. So if your pipeline failed because of access permissions, you can go ahead and retry it now that we've added the variables in, and maybe it'll work. But you have to remember that just adding the variables in alone won't do the trick. And what we actually need to do is to actually use the service password. So let's go ahead to the GitLab YAML. And we're gonna go ahead and let's see here. Where is my skim? So before script here, you can go back to the tutorial in the browser so you can see what I'm doing. Right here. We're gonna run this line in. So we're gonna want to do printf service pass base 64d knet cern user as cern.ch. And now that we've added that in, we can go ahead and just GitLab and then commit knet for access control. And then should work. And that should just work, but for those of you who are using publicly accessible files, you won't notice anything different. But now that we've gone ahead and we've just used these custom environment variables in our CI job, and that's pretty much it. Alright. And so that's it. For those of you who are in it for the access control, that's all we had to do here. The very last thing that we need to do is to add artifacts. So as you can see here, we want to add artifact to the scim.ggh, which saves the scim.ggh.root file and will expire that artifact in a week. And that should do the trick. And we'll go ahead, stage, commit, and push. And if I refresh here, we should have everything working. That looks great. Alright, so everything should be working, and that is entirely it with environment variable. If you have any more questions about this, you should look at these helpful links that I provided here. Note that service accounts will provide this extra layer of security between the outside world and your account, and environment variables in GitLab CI CD allow you to hide this protected information from others who can see your code. And if I can go in here, because we added the knet for access, I can look in here and see what's happening. And that's still running. And you can see that once the log file expands, we won't actually see the Kerberos password showing up in here at all. And even if it did, you couldn't echo it out directly because it got masked, as you remember. And so that's the nice thing about using these environment variables. It also makes your code a little bit more generalizable so that you can fork this and set up your own environment variable with your own username and password, and things should genuinely work. Let's go ahead and wait for these Docker images to pull. There's always such a large Docker image. Let's see a slow train in the meantime. Alright, so you can see here that it throws in the password for it, but you can't see it at all. And we're good to go. So things are running. Alright, so that's it for this section. We've just finished talking a little bit about getting the skimming head stuff, as well as a little bit about environment variables. Now we're going to talk about actually making pods, because that's going to be another thing that we want to do. We've already created a job that compiles our skimmed binary. We've created a job that takes the skimmed binary and creates a skimmed root file. Now we want to make plots from that root file. So this is a little bit starting to become a little bit more on your own, because at this point you've learned everything you need to do. However, I will show you the command that we need to run here. This command is python histograms.py. We pass in the skim ggh, we specify ggh, and then we want to create a hist_ggh.root. So we should add it to our GitLab CI YAML file, and there's nothing else in this tutorial, so let's talk it through here. So, back to our CI YAML file. So, we need to add artifacts. But of course, we need to add in a plot stage. So, that's our first step. Let's call that a plot stage. We need to add in a plot ggh job. Let's see here. We would want to do the script python histograms.py. What was it? Python histograms.py skim ggh.root ggh hist ggh.root. Great. That doesn't look too bad here. And let's see here. Artifacts. Paths. Hist ggh. Because we need an artifact, right? Expires in 1 week. Expire in 1 week. Alright, so this is pretty much all we need to do, which doesn't look too bad. Also, I'm wondering about this image that we need to use for the planning job. It looks like I didn't give myself any hints here. Looks like we shouldn't use the hello world job. So let's go ahead and delete the greeting stage and get rid of the hello world. Alright, so this image here I didn't really specify anything about. So I wonder if I can just use a Python image. But let's look at histograms.py and no, so you can see it needs root. So we still need to have that root image. That's fine. So I will just go ahead and add in the image line here. Root project, root conda 6.18.04. And is that all I need to do? Nope, because I need to specify the plot stage here. And then I need to tell it to grab the right skim ggh file. So I need to specify the dependencies, and it's the skim ggh job, which makes the skim ggh artifact that I need. Am I missing anything else here? I have the plot stage, the dependencies, specify the image of the script, which should just produce the output, and then I have artifacts for the output for the path that expires in a week. So I guess this is just another script with another job, another stage, and another artifact. Another script, job, stage, artifact. Let's see what those changes were. So that looks pretty good, and that looks pretty straightforward to me. So we'll still have 3 stages, and we will have, I believe, 4 jobs over 3 stages. So let's see what that looks like. And I guess this time, since it's starting to be a little bit more complex, we can go ahead and look here. Alright, so build skim and build skim latest are being running parallel first in the build stage. And then we'll go ahead and skim that. And then we'll go ahead and plot that. And the plot will store that artifact as well. And we want to do something with the artifact, which I think I'll save for the next video. So let's go ahead and wait for this to finish. just so that we can see what things look like. You can see that we've been adding artifacts for some of these previous jobs as well. So now we're able to download artifacts at a given point in time, which is fantastic for us. Alright, looks like this is almost done. So we'll hang on while this finishes up. Let's begin and see what this is. Of course, it's still pulling the Docker image. One thing that I might as well point out is, we're not quite testing anything yet. I mean, on some level, we are checking that the code compiles, which is a good thing. We are checking that the code runs, the skimming code, which is also a good thing. We're also checking that we're able to plot histograms, root histograms, using the Python script, which is also a good thing because maybe you change the Python script and you still want to be able to make sure you get the same output. Perhaps you refactor or add in some new functionality or change the style. All of these, yes, in a way, are you're actually testing something. But are you actually testing against physics? Not necessarily. But that's not a problem right now because testing code is an important part about having reproducible physics. So skimming is happening right now. Let's peek into that. And again, it's pulling these Docker images. Xeon has a lot of shared runners, so they don't all share the cache for these images, so sometimes it takes a little bit longer than you expect. I mean, so far everything runs in under 2 minutes, which I'm pretty happy with. It just means that for a tutorial video like this, there's not a lot you can do to fill in this silence. It looks like it's processing things okay. It processed the input. Alright, upload that artifact and okay. Let's go on to the next job in this pipeline, plotting. Let's watch it go. And hopefully it should work. What else could I talk about as part of the tutorial? Not much. I mean, so far the tutorial's been doing a pretty good job, especially after all this time. You expect by now something would break. But I guess it hasn't, which is a good part of the continuous integration, because I get to test out this tutorial from time to time. Alright, so it should start running any time now, because it generally takes about 45 seconds to a minute 15 seconds for the Docker image to pull. There we go. And then it starts running the Python script. It looks like it produced some histograms, which is great, and so all good to go. And this job passed, and therefore this entire pipeline succeeded. And that's the end of this section. The last video on the series of CI CD tutorials that we have here. And honestly, at this point, there's not a lot left for you to do other than to talk about actually making a test for physics. So let's go ahead and look at what we need to do. So at this point, there's just a lot of code here to copy and paste. So we're going to go ahead through this last test, make a test for real section, and see what we need to do. So our first step here is to add a regression test. And so I've explained sort of in words what I need to do to myself. So I see here there's not a lot left. So let's go ahead and open our GitLab CI YAML file and see if we can implement all these changes. So it says here, I want to add a test stage after the plot stage. Let's do that. Next, we need to add a test job, test GGH. test GGH part of the test stage and has the right dependencies. So obviously that's going to depend on plot GGH. And interesting, looks like we want to grab the log file too. I wonder why. And in this case we probably want to parse that log file, because if you go back to some of the previous jobs that we've had here, where is it? The skimming job. Let's look at that for a second. You can see some of the output here is that it actually prints out some cut flow information. And that's useful information that we want to check again to check for physics or check for physics changes. And I guess our first attempt at this point, given this existing code we have, is to just check the log file has outputs that we expect it to, which is fine. Alright, so let's go ahead and add in the skim GGH dependency as well as the plot GGH dependency. Now that we've added the skim GGH dependency, we should go back to here to where skim GGH is, and we're gonna go ahead and dump that into a skim GGH.log file. And then we're gonna go ahead here and let's see here, add in the artifact, which is fine. And let's see here, we have histggh.root, we're good there. Okay, and it looks like we've finished up everything we need to do in the YAML file, I think. Almost everything. So let's quit out of that for a second and make a test directory. In it, we need to create two Python files named test cutflow ggh.py, and what is the other one? Test plot ggh.py. And looks like these are going to use pyroot and pytest. And we've included some lines in the tutorial here that we can copy paste in. So let's go ahead and look at this. So here's test cutflow ggh.py, and this is a lot to type in, so I'm just going to go ahead and copy paste it in. And this looks like it's parsing the log file that we create here, skimggh.log, and it's going to parse it line by line and check that the lines match. So that looks pretty good. It's just going to look for the fact that these lines exist in the file. That's pretty great. Alright, so I'm going to go ahead and add that test cutflow ggh. We're going to add that test because that test is done. Alright, we have a template for test plot ggh, and let's copy paste that in and talk about it. So this one looks like it's using root, pyroot. It's going to open hist_ggh.root. It's going to look for particular keys in that output histogram, particular histograms in this case. And if it can't find those histograms, it's going to exit 1, a failure. And then in this case, it's going to integrate the GGH leading PT histogram here. And if the integral of that histogram varies too much from this value, this truth value that we know about, then we know that the physics has changed in that histogram. And that's an important thing to keep track of. And that means when the physics changes, we've identified some sort of regression. And that's a very good kind of test to have here. So that looks pretty good, and if it fails, it'll exit 1 and we're good to go there. Otherwise, the script will exit 0 by default. So we'll go ahead and add in that test. So we need to be able to run those tests. So the way we're going to do that, for example, is likely with just running Python, I believe. If we look at the test cut flow that we have here, it looks like we just run Python on it, right? I should just be able to, sorry, Python 3 test cut flow. Yeah, and it looks pretty good here. Alright, so, I'm gonna go ahead and make this work. So, it looks like this uses Python 3. I noticed this because of this print statement here, which uses a format string. So that should be pretty good. So, what else do we need to do here? Let's check this other test just to see what that looks like. The plotting also looks like it should just work out of the box as long as root exists. So yeah, all we need to have is root existing and we're good to go there. Alright, so we need to go back to our GitLab YAML file and we need to use the same root conda image that we've been using all along. I'll copy that in. Alright, and we need to write a script here that runs these tests for us. So we'll go ahead and do something like, say, Python 3 test. What are the file names? One of them is test cutflow ggh.py, and the other one is Python 3 test plot ggh.py. And let's see how that works. Alright, test plot, test cutflow. Okay. We need to add the GitLab YAML, and then we can go ahead and see what the stage changes are. And things look correct. That adds the 2 new files, and it adds the test job. We're adding a test stage, and everything looks right. So things should just work. Add regression test, or maybe add test on physics. And we'll push that and see how things go at this point. And now you can see that we have 4 stages now. We've got the build stage, we've got the run stage, we've got the plot stage, and we've got the test stage. Now I'm a little bit curious at the moment whether or not this root project image that we've been using had Python 3 on it. Hopefully I've been smart enough. So you know what? Why don't we try doing this? Docker run. Actually, you know what? You're gonna learn about Docker in a later session, so I won't talk about that for now. We're just gonna go ahead and patiently wait for all of this to finish up. The build stage already happened. Wow, that's fast. Perhaps the run stage will be fast too. So we're just waiting for this Docker image to pull right now. So we'll just wait and be patient. There are lots of different things that you can do at this point. You've understood a lot of the basic CI CD features from pipelines, stages, jobs, being able to compile, being able to debug, being able to play around with the various different features of GitLab itself, being able to navigate. You've been able to, add environment variables to these things. And then you've been able to run Python code, been able to run compiled C code, and then use artifacts and pass things around from time to time. So that's been a lot that's been going on so far. So I think that's a pretty good use of time here. So let's see what happens in the next few jobs that come up. It looks like, look at that. Sorry. It looks like skimggh.log was also created, which is great. So let's go ahead and look at the plotting. and watch that go. So, I mean, if you look at what we have here so far, we built this all from scratch in just basically, under 3 hours without too much of a pain. So the whole point is that it should be pretty easy to do everything you need to do for whatever you're looking at. Let's go ahead and look at what this test stage is doing now. I'm kind of half expecting it to fail at this point, and it does. And look at this. It's not able to find this line in the file. Integrated luminosity is 11467. And you'll see here that this log file is 114467. So it looks like we have a typo in that script. So this is in the test cutflow script, right? Where's the integrated? Right here. So we're gonna 114467. So let's update that line. So it failed, which is great, but we should go ahead and fix typo in Python and cutflow check. The stage commit push, and let's just do that all over again one more time, just to be sure that we've got everything going. Hopefully these will run a little bit faster, since at this point we should have hit enough runners that they've all cached this root project image for us. It looks like we've got a runner with a cache here, so it's hit this and it should run a little bit faster. How fast does it run? Let's see here. Alright, let's move over to the run, which should be running now. Yep. Things are running pretty fast, which is nice. Alright, let's move over to the plotting stage. Hitting a lot of runners with caches, so that's going to be one of the fastest pipelines we've had. It's always very nice when you can make a computer do everything for you. Alright, we're already on the test stage now. Let's see if this works. It failed. And you can see now that the integral of GGHPT1 is different. So it looks like the integral has changed a little bit. So maybe we should go ahead and fix it, or understand why that happened. So it looks like I'm somehow off by a factor of 2 in this integral, a factor of 10, order of magnitude. That's probably somewhat expected depending on how many events I ran over. So for now, we're going to go ahead and update this just to get the job working. But you can see it looks like the cutflow test passed, which is great. So we just need to get this one passing. Fix typo, maybe? Perhaps it's a typo. In the GGHPT1 integral. Let's go ahead and do this one last time to finish off this entire tutorial. So, at this point, now that we have everything in place, you can imagine that the next thing to do is to try to do the same thing for a project that you have in mind. a project that you already have existing but you don't have any CI for. Maybe you already have some CI implemented on a project you collaborate with other people on. And you can look at that, maybe figure out a way to refactor or improve or clean up in a way that you don't have to repeat yourself too much. There's lots of different ways you can do that. Or, sky's the limit at this point. There's a lot more that you can do with this, and we've only ever covered the basics here. Is the skin job running? I wonder what happened with build latest. Oh, maybe that's slower. Yeah, it looks like we hit a Docker runner here that's taking a little bit longer because it doesn't have a cache. Alright, should be any second now at this point. It usually takes about a minute 30 or so from what we've seen from experience when we hit a runner without a cache. Alright, so let's skip over to SkimGGH. Alright, and that's triggered and running now. That already hit a Docker. That already hit a runner with the cache. That's pretty fast. Look at that. It looks like it's going to be running in just under 30 seconds for this entire thing, maybe? I'm not sure. Definitely under a minute by this point. Oh yeah, look at that. 29 seconds. It's pretty fast. Alright, let's see what the plotting is doing. Man, CERN has so many shared runners, so it's just a bit of luck there. Hopefully you have better luck than I do some of these days. Let's be patient. Here we go. So this is it. We're just about to see if our test job runs successfully. Let's jump over to that stage. Oh, we got lucky here. So do we now get to finish everything completely? It looks like we do, and we do have a successful pipeline. And that means at this point, I'm happy, and we've been able to add CI to the project. I can go ahead, click edit here, remove this work in progress prefix. Oh, sure, yeah, I'll squash commits. We'll go ahead and save the changes. And this is ready to merge. So we click that shiny green button, which only shows us shiny green because the pipeline or the jobs in the last pipeline have passed. And we click merge. And with that, we are done with this tutorial section.